Note that these are not FDA approved or have CE mark and are therefore investigational. Most people, when we look at the most common approaches for PV isolation, we look at point-by-point ablation. It has clear advantages in terms of the flexibility of the lesion set, as well as site-specific titration of energy. The main disadvantage, of course, is the technical expertise and the prolonged procedure times attended with this approach. Balloon ablation, on the other hand, has the advantages of the technical ease of use and relatively quick procedure times. But the disadvantage is that it cannot titrate power directionally and has a limited lesion set. So in this context, this novel lattice tip catheter, which is a temperature control catheter, asks the question, can you get the advantages of both? Can you get the flexibility of lesion set without sacrificing ease of use? And can you get quick ablation times without sacrificing site-specific energy titration? So what I'm going to report today are results as part of a clinical trial. It's a non-randomized first-in-human feasibility and safety trial where patients are enrolled at 2 European studies in Homolka Hospital in Prague and Vilnius Hospital in Lithuania. Of course, local ethical committee approval as well as the country-specific regulatory approvals were achieved. And then the goal of this particular presentation is to report on the acute outcomes of patients undergoing pulmonary vein isolation as a first-ever procedure. The procedure details, in usual fashion, transseptal puncture with the goal ACT. A deflectable sheath was used in these procedures. An intracardiac ultrasound was used in these procedures. The system itself consists of the catheter itself, which is an irrigated temperature control catheter, a generator and infusion pump, as well as a corresponding or dedicated electron pump mapping system. In terms of esophageal management, either temperature monitoring or esophageal deviation was performed. PV isolation was performed in all patients, and other lesions were as per the operator preference. This is the system itself. There's the catheter. It's an 8 French catheter with a compressible nitinol tip. It has 9 nodes, each of which contains a microelectrode as well as a thermocouple. What you see is one at the tip, 4 more distal, and 4 more proximal. The whole nitinol mesh delivers energy, and there's irrigation from a central jet. There's an integrated pump and generator as well as the mapping system. So let's take a look at what's probably, I think, the most unique aspect of this catheter, which is the large thermal footprint that it utilizes. Compared to a standard catheter, if you do an ink blot test, you see that the surface area of coupling to tissue is substantially greater than regular catheter. And interestingly enough, not much change as a function of contact. I mean, of course, you have to have contact, but once you have contact, pushing harder probably doesn't make much difference because this is somewhat compressible. I should say probably makes less difference. Fair comment. If you look at current flow, if you're delivering 50 watts, it's about 0.7 amps, versus with this catheter, it's substantially more amps. But given the difference in surface area, the effective current density is actually much lower with this lattice tip compared to standard. And certainly if you're delivering 90 watts, it's substantially less. The lesions themselves in the atria are between 2.5 to 5 seconds long. This, I'm just going to take you through this. This is actually the mapping system itself. So the same catheter is utilized to create a mapping system, and there's a magnetic sensor to localize this particular catheter. So here it's collecting voltage information. This is where we had previously isolated the right vein, so you see low voltage over here. Just jump forward in the interest of time. And you can see, just like most mapping systems, it can be used to create a electron map. Then let's move forward to the ablation. So what you're seeing here are the microelectrodes. As you step on the pedal, there's a cooling phase, and then as the energy is delivered, you see the blush of heat that's reflected and sensed, I should say, by the electrodes. And you see how the electrograms disappear. The electrograms, step on the pedal, cooling, then the energy is being delivered, electrograms disappear. Again, in the interest of time, this is sped up now 4x, just to keep things moving along here. And you can see as you move it around, again, you move to all the locations. Now, and remember, because this catheter also has microelectrodes, you can use the same catheter in order to verify that the veins are isolated. In the initial cases, after the veins were isolated and confirmed with this catheter, we would then take a lasso catheter. But frankly, after a couple of cases, it was pretty clear that this catheter works well. So we didn't necessarily use the lasso on all the patients. And then here, it's going to be pushed in, and there's no electrograms. Of course, I didn't show you the electrograms beforehand. You just have to trust me that there were some. This particular case, delivery time was 43 seconds, and transpire time, meaning the time from the beginning of the first lesion to the end of the last lesion, was just over 3 minutes. These are the patients, mean age, evenly split between male and female. You can see comorbidities. You see that about half the patients were under general anesthesia, the remaining under sedation. And in terms of the esophageal strategy, half were with deviation and half were with temperature monitoring. The LA mapping time, you can see here the mean and the median. Because of the relatively small number of patients, I'm showing you the median also. This is the number of lesions per patient, about 35. The RF time, 135 seconds. That's the total amount of time when the energy was on. The therapy duration time for the individual lesion sets for the left veins and for the right veins. The fluoroscopy time, relatively small, though in reality I think this could be done completely fluorless. And the saline, amount of saline that was infused is shown there. From a safety perspective, there were no acute safety issues, including pericardial tamponade, esophageal complications, and stroke or systemic emboli, phrenic nerve injury, or other complications. Limitations, this is a limited number of patients with relatively few centers and relatively few operators. I'm only showing you acute procedural data. We still need to understand what clinical outcomes look like over 1 and hopefully longer year follow-up, and probably most importantly, we need data on the durability of the isolation. And obviously, the small size of the data set limits any sort of conclusions in terms of safety, but at least the early data looks promising. The abstract was, we only collected data on PV isolation, and that's what I'm reporting in this abstract. However, I'm going to show you just two slides of other sort of interesting aspects. One is the mitral resonance line. Here you see, actually let me run this because this is worthwhile. So here's the catheter, we're CS pacing. You can see the electrogram here. We go on with energy, there's a lesion, then the catheter is brought back, and I'm going to jump forward a little bit. Here again, you see the electrogram just after the pacing spike, go on with energy, and you see the impression that it just got split. And I'll come forward here. We put the catheter on the other side, and you can see the timing from the CS pacing to here has prolonged. You can also see this arrow that shows beat-to-beat activation as sensed of the electrodes on the surface. And finally, we can pace from this catheter, and you see a reversal of CS activation. Proximal is first, distal is late. This particular case, RF delivery time was 44 seconds, and transpire time 4.5 minutes. And actually, the actual preclinical and clinical data we have as a poster, if you're interested. I think it's actually up there probably right now. Similarly, we have experience with the CT isthmus line. Here's another example. You're looking at actually it's a superior, it's actually an inferior view, and this is an RAO view. It's interesting, I didn't show you this before, but for those of you that use intracardiac ultrasound, you can see the tip of the catheter very easily. It's very refractile and easy to determine where the tip is as opposed to seeing the shaft. In this particular case, again, it should be CT isthmus line, but it took 24 seconds of RF delivery time and just about 2 minutes of transpire time. And you can get more information on the posters, which is downstairs. Finally, I'm going to show you one slide. This is of a patient that we brought back for a second procedure. And again, this is an N of 1. This isn't data. This is simply a single case. But what you see is that the veins are isolated, and with CS pacing, distal CS pacing, you see that the mitral line that we had previously placed appears to be blocked. So I do believe that this is the next evolution of point-by-point electrogram mapping. The tip recognition on ice is really unparalleled. It's a large thermal footprint that potentiates both shallow lesions, so at times when there was only esophageal temperature monitoring, we'd do 2.5 seconds, or when we're not worried about the esophagus, either because we're anterior or because we deviated the esophagus, we'd give 5-second lesions. I think one of the most interesting aspects of this catheter, which is hard to appreciate unless you use the catheter, is its stability. The catheter, probably because of its compressibility and its topography, really has a tendency to stay where you put it. You tend to see less catheter slipping and sliding as we oftentimes see with our standard catheters. There's obviously a number of questions to address, including the durability of the lesion sets, the safety and efficacy in a large multi-center study, and of course, as Elad had asked earlier about the other technology, could this be useful for scar-related VT ablation, which I would argue is truly an unmet clinical need. Thank you very much. Catheter, which I don't really like the name of, but it tells you it's 9 millimeters once it expands. And I should say it's a self-expanding, so it's a nitinol mesh. So you basically just push it through, and then when it comes out of the sheath, it goes to its native state.
And then the irrigation force with the catheter is what about?
Oh, the flow rates. Oh, now you're asking me tough questions. It's about I think it's 4 cc's during mapping, and then actually the flow rates change depending on what the surface temperature is. So it varies, but I think it goes up to about 20 cc's.
Actually, no charge been detected.
We have not detected, as with any catheter, you can make char. If you drive the power high enough and you don't have adequate flow rates, we can clearly make it in the preclinical models. but the system has obviously been optimized for that. And again, we have 17 patients. We need a lot more patients to understand whether or not that continues.
I have one quick question for you, Vivek. You were part of the development of very important technology, including force sensing, irrigated catheters, and a big proponent of the point-by-point ablation over the last decade. So, and also, the ability to use these catheters in the context of reduced ablation or minimal ablation. So, having those two elements in mind, the contact force and the lack of fluoroscopy in most of these cases, where do you see this technology and where do you see the point-by-point going forward?
Yeah, it's funny, as I've been lucky to be involved in this, I've gone back and forth. There was a time I thought, oh, one shot's going to take over everything. And a time when I thought, no, the flexibility of point by point. And I have to tell you, I'm going back and forth still. The reality is both sort of approaches have really advanced aggressively and impressively. I think the most important thing about point by point, what I'm getting to in my mind, is that catheter stability is so important. And I guess I only appreciate it now that I have a catheter that gives you such great stability. I think that's the most important aspect, and given that, I think it's going to be a close call. 5 years from now, I think it's not going to look much different than now. There's going to be a camp that wants one shot and a camp that uses point by point.
And Pierre, thank you very much. Apart from the mapping, the ability to base and map and everything else, when you show the lesion, the contact was not, giving any difference. I mean, how do you envision this catheter different from, the Q dot or the Epix Medtronic? I mean,
yeah.
The concept is the same. You don't need force, you need contact. So,
right.
How do you envision?
Yeah.
Where's the difference?
It's funny, every time we achieve something, we see the next thing we don't achieve. And what I see is catheter stability as the issue. I'm sorry, I keep saying the same thing because I think it's so important. The advantage of short duration lesions is that they're short and you deliver a lot of power. The disadvantage is that if you don't have stability, then you're not going to make a great lesion. So that's the issue. I think short duration is great provided you have stability.
Okay, thank you.
Thanks.
So we're going to move forward with our next speaker, Dr. Romero.